Wait a minute and then we'll begin. Hopefully I can play the sounds. Okay, folks, I have a request for all of you. Please, and on Zoom, type in your actual names so I know who is in the class and I may just call out to you. So instead of having just your Andrew ID, uh, please have your, I think you can change your ID on Zoom itself. All right, let's begin. Again, just to confirm, everybody can hear me, correct?
Yep, I can hear you.
All right. So when I ask you questions, do me a favor, please at least give me a thumbs up or thumbs down so I can watch for your responses. And I know if you're understanding or you're following along. This is kind of important for me to be able to know how well the class is going. Also, do voice your questions if you can. Otherwise, put them on chat. I have the chat box open and I should be able to follow it, right? Okay, let me begin. So again, picking up where we were last yesterday, we are going to be going over the basics of linear algebra because most, if not all of MLSP is linear algebra. Now, all of you have almost certainly gone through lots of linear algebra in your college uh, syllabus and in high school. So much of what we will be talking about in today's lecture and in the next lecture on Tuesday is probably not going to be remarkably new. So we won't be posting poll links. I'll just ask you questions during the lecture. It is unfair to be posting poll links when in a makeup class. So anyway, the hope here is that in going through this lecture on linear algebra, you will nevertheless learn something new on how to think about some of these things that you have previously encountered in your academic work. So let's begin. The book that we will follow is, or the book that I highly recommend everybody looks at, is The Fundamentals of Linear Algebra by Gilbert Strang. If you can, please also go look at his lectures. They're up there on MIT OpenCourseware. It's very important to be comfortable with linear algebra for not just this course, but in general in life. And so, it appears repeatedly in the form of eigenanalysis, singular value decomposition, just solving simultaneous equations and what have you, in pretty much every problem where any kind of mathematics is applied. In today's lecture, we're going to go over a bunch of definitions, which is essentially a small subset of everything that is typically used in machine learning and data science, but it's an important subset. And the intention is that you will recollect things that you might already know, or maybe learn something that you didn't. So before I begin, do we have any questions? Any questions? No? Okay. So why do we use linear algebra? Linear algebra is about manipulation of data, of vectors, and we encounter these everywhere. Now, there's nothing special about vectors. They're just on matrices and such like. They're just ordered collections of numbers. So why do we like to use linear algebraic notation and think about it in algebraic terms? for multiple reasons. It simplifies notation, like we show over here, up here, trying to have this double summation, summation j, yj, summation I, xi, aij. This is ugly. If I were writing this in linear algebraic terms, I just write x transpose ay. So much simpler. And that also translates into much simpler code. But the real magic of linear algebra is that it gives us intuition. It tells us ways to look at things that you couldn't intuit by looking at this multiple looped equation right here. And there are lots of things you can do in linear with algebra. So consider this. Why am I not able to do this? I should be able to. For some reason, this pointer is not letting me. Okay, so consider this little video, right? It's showing a very colored object rotating. Believe it or not, that entire operation is just linear algebra. And algebra can capture things like rotation, projection, scaling, perspective. It allows you to manipulate data, extract information from data. Here's an interesting decomposition. Here's a piece of music. Can you hear it? Did you guys hear it?
We can hear it.
Yeah, okay. So it's a little bar from Bach's Fugue in G minor. It's got 5 notes, of which 1 note is repeated twice. And just a very simple linear algebraic manipulation will tell you that this little bar is composed of these 4 building blocks. The first note. The second one. And believe it or not, the fact that the 4 notes in this musical bar were the 4 that we just played, including the fact that the second note was played twice. All of this was extracted through pure linear algebra without any reference to any music or any prior knowledge of music. All we did was algebraic manipulation of a bunch of numbers that are shown by this visualization, which is the spectrogram over here. So that's the power of linear algebra. And so we're going to learn how to do all of that later in the course. But for today, we're going to look over vectors and matrices, what these things are, what kinds of operations you can perform, various types. We're going to look at some properties of matrices, determinants, inverses, and so on. And in the next class, we'll look a little more at solving simultaneous equations, what it means to project, what is eigen decomposition, and singular value decomposition. Again, all of these may seem familiar to you, but then again, at the end of this class, I do believe that you might think that you've learned something new because we are looking at it differently from the perspective of data, right? And signals. So let's begin with vectors and matrices and some basic matrix and vector operations. Even before I do this, let me ask you a question. What is a vector? Does anybody want to answer what a vector is? So Aisha, what do you understand by what a vector is?
Is that me?
No, that was Aisha Nuhu.
Oh, sorry.
So I think when we say a vector, it's like kind of like a representation in a certain space.
So anybody else want to? Yeah, that's a pretty good definition. Mohammad Al-Faraj, do you have an answer? Do you have any other definition for this? Yes.
I just joined, so I'm not sure what the question is, if I'm being
So
honest.
how do you understand what a vector is? What is a vector?
I would define it as a collection of numbers that may be connected in different ways, but it's a convenient way of grouping together numbers in a way.
These are all good definitions, right? From our perspective, a vector is just an rectangular or horizontal arrangement of numbers. Perfectly good answer. So if I arrange them vertically to get a column vector, this is an n cross 1 vector. The n represents the number of rows. Here that's 3. And the 1 represents the number of columns, which is just 1. So it's an n component column vector. This figure to the right is an n component row vector, right? You know what these things are. But without additional context, these representations of numbers don't really mean anything. A vector, just an ordered arrangement of numbers, is a meaningless mathematical object. We have to assign meanings to these components for us to make sense of them. So if I said, for instance, that this vector ABC represents the height, weight, and age of a person, arranged like so, then it begins to make sense. And immediately you also see that the order in which it's presented makes sense. If I call it BAC is a very different vector than ABC. Now, from a mathematical perspective, a vector actually represents a net displacement in space. So when I give you a vector ABC, then this vector ABC represents how much you would have to travel from origin to a particular point in space. And so each component of the vector actually represents the number of steps along a basis direction. So when I say vector ABC, this vector ABC actually represents A times some basis vector X plus B times some basis vector Y plus C times some basis vector Z. And as you can see, there's an issue with this definition. And what might that be? Anybody want to take a guess? Isaiah?
Sorry, I don't have a good intuition.
So it's kind of circular, right? The definition is circular. Just give me a second. Because I'm defining vectors in terms of vectors. And so you have to understand, you have to come up with some common consensus. Without defining what X, Y, and Z are, this whole thing makes no sense. I'm defining a vector in terms of vectors. And so without reference to this X, Y, and Z, this vector makes no sense. Now, very often when I just say ABC, this X, Y, and Z are implicit. We just agree upon them and we don't have to mention them at all. So a vector 5 to 13 represents A times some 5 times X plus 2 times Y plus C plus 13 times Z. So what are these X, Y, and Z? In the most basic, in the standard interpretation, we just assume that the underlying implicit assumption that these bases are a set of unit length directions or unit length vectors. Again, the self-referentiality cannot be bypassed over here, with the understanding that these three are all orthogonal to one another. So each of the bases is going to represent something of the same length. Each of them has the same length, and the three are at 90 degrees to one another. And so when I say so, then this vector ABC says that I'm going to, this represents a location in space, which is A times, or the vector 5 to 13 is 5 times the vector X. So you take 5 steps of length X along the first direction, plus 2 steps of the length Y along the second direction, plus 13 steps of the length Z along the third direction. So it's kind of, and all the bases are assumed to be unit length. This is when the bases are not explicitly mentioned. The implicit assumption is that all the bases are the same length, that their length is a unit length, and that they're all orthogonal to one another. Did that make sense to you guys? Yes or no? Just give me a thumbs up if it did. Right, I see, okay, 7 of you. So what about the rest of you guys? Sunrita, did that make sense?
Yeah.
Okay. But then I can change my bases. X, I can say ABC can also be A times X plus B times Y plus C times Z. C times Z, these are the standard bases, but it could also be something else times where X, Y, and Z could be something else, right? So and then the location indicated by ABC can be entirely different. This means that, consider this location over here. The vector, as I said, represents a location at some point. So this guy over here can be obtained by taking 5 steps along the orange direction, 2 along the blue, and 13 along the green. But it can also be taken arrived at by taking some 3 steps, 3 times this green vector over here to the right, plus 2 times the blue vector, plus 3 times the orange vector. In which case, this vector ABC is going to be very different from DEF if my bases are different, and yet both of them represent the same location in space. So when I'm not using my standard bases, I have to specify what my bases are. Without that specification, the vector makes no sense. There's a notion of a length of a vector. And the length of a vector is basically, if I assume standard orthonormal bases, meaning that my bases are all length 1 and at 90 degrees to one another, then the length of the vector is the Euclidean displacement from the origin to the point that you will arrive at if you traveled A times X plus B times Y plus C times Z. And of course, now this is all very nice when I'm thinking in the abstract. From a signals perspective, what does this mean? Signals are frequently going to be represented as vectors for manipulation. For example, if I have a segment of an audio signal, it's going to be a bunch of numbers. We've plotted this before. But for us, it's going to be a vector, which is just an ordered sequence of numbers. So signals are frequently represented as vectors. Or if I look at individual segments of a signal is often represented as a spectrum, where the spectrum represents the energy in a bunch of different frequencies. And so now the vector representation of the same signal has a bunch of components where each component represents the energy in one particular frequency. So these are 2 different vector-based representations of the same signal. Now, images too can be represented as vectors. Here's a picture with 3 Pac-Man. This is a 321 cross 399 grid of pixel values. I can unroll this picture into one long vector. Every pixel is either 1 or 0 because it's black and white. And so this picture is going to become a 128,079 component vector. And that's just this guy unraveled. If I have to fold this back into the image, I will have to recall how I unraveled it into the vector. So I don't know if I've conveyed the notion of a vector properly, but I do hope that you get an idea of how signals of different kinds can become vectors. Questions? None? Okay. So you can operate on vectors. The simplest operation is multiplication by a scalar. When I multiply a vector by a scalar, basically every component of the vector gets multiplied by a scalar. So if the vector 3, 4, 5 gets multiplied by a scalar 2.5, now this is going to be the vector 7.5, 10, 12.5. So if you think about it, this vector 3, 4, 5 said, I'm taking 3 steps along X, 4 along Y, and 5 along Z. So when I multiply by 2.5, it means I'm going to take 3 times 2.5 steps along X, 4 times 2.5 steps along Y, and 5 times 2.5 steps along Z, which is why you end up over here. You're just basically scaling each component. You can add vectors. When you add vectors, the individual components add. So for example, if I added the vector 3, 4, 5 to the vector 3, minus 2, minus 3, then each component of the first vector is added to the corresponding component of the second vector. So the sum becomes 6, 2, 2. Now this can also be interpreted in terms of bases. This vector says you're taking 3 steps along X. When you add the second vector, you're taking an additional 3 steps along x. So the result is 6 steps along x. So also you're taking 4 steps along y, and then minus 2 steps along y. So you end up with 2 steps along y, and so on. It's a component-wise addition. Now, so addition and scaling are simple. There's a third notion, which is the inner product of two vectors. If I have two vectors u and v, say u is this vector abc, v is this vector def, then the only time when I can, this is convention, the only time I can take an inner product of u and v is if the first vector is laid horizontally and the second vector is set up vertically. And then the inner product is a times d plus b times e plus c times f. It's a component-wise product of these two terms, of the corresponding terms, and then a final sum. So the result is going to be a scalar. This is also called a dot product. Again, nothing new, right? But then, the inner product of a vector with itself is the squared norm. It's basically the square of the length of the vector. So the inner product of u with itself, which can be represented as u dot u, which is basically u transpose times u, which is how you get a row vector multiplying a column vector, is going to be a squared plus b squared plus c squared. That's the squared norm of the vector. So far, so good. But what does this inner product really mean? It actually tells you how much one vector explains the second vector. So so for example, consider you're in New York, you're at this orange location here, and you want to go to this point A, which is coordinate 200, 1600. So, this is 200th Street, 1600th Avenue, whatever, right? But instead you had one too many. So instead of going this way, you sort of wandered off and ended up at this point, 770, 300. Is everything lost? Are you completely screwed? No, what math will tell you is that even though you've ended up here, you actually made some progress towards your original destination. You managed to get this, you managed to close the distance to your original destination by the amount shown by this orange arrow. And so this, how much you managed to close the distance, is given by the inner product. Specifically, it's going to be the inner product between A and B, where A itself has been normalized to unit length. So you managed to progress 393 yards towards your original destination. Now, from a signal perspective, it gets more interesting. So here are 3 notes. This is me playing a note on the note C on my harmonica. Now imagine that for some, I find myself with a harmonica where the note C is distributed. The note C is as the spectrum. It shows the various frequencies and the energy in the different frequencies. So I decide to fool my audience. Whenever I must play C, I play the note E instead, which is this guy. Can I get away with it? Will it sound okay? Anyone? If instead of C, can I just play E? What do you think, Akansha?
I don't have an immediate answer. I'm still thinking.
Okay, so let me play you another one. Instead of C, I play the same C is present in the next octave, which is this guy. If given a choice of either playing E or C in the next octave, which must I choose to replace the original C to have the least distorted effect? Anyone familiar with music will be able to tell me. But Ching Zheng, what do you think?
Sorry, I'm not familiar with music.
But
Sorry.
if you were to take a guess,
I'm not sure of that.
anybody else? Does anybody want to take a guess? Vidur, what do you think?
C2.
Why?
It's the same frequency.
Is the same note, right?
Mhm.
You are correct. If I can't play the first C, if I play the same note in the next octave, it's going to be less disruptive than if I play a completely different note. Can I get a mathematical explanation for this? And then for this, I can actually look at inner products. So each of these nodes is a spectrum, which can be represented as a vector, right? If I look at the inner product of C and E, that's just 0.1. Whereas if I look at the inner product of C and C2, which is the same note at the next octave, that's 0.5. So if I'm trying to fake C, these numbers will immediately tell you that I'm much more likely to get away with it if I play C2 than if I play E. Now, is there a physical reasoning behind this? The C in the next octave is one where every frequency has been doubled, which means that if I align this spectrum up against this spectrum, if I try to align C against T, none of the frequencies would match. The base fundamental frequency of E is different from that of C, and every harmonic of E is also going to be different. But then if I look at C2, the fundamental frequency is doubled and every harmonic is doubled, which means these frequencies will have corresponding matching counterparts in C, which is why this guy is a closer approximation to this one than E is. And that's what the inner product is telling. Did that make sense to you guys?
Yes.
So I see 2 thumbs up. What about the rest of you? Did that make sense? All right. And so that's what an inner product is. I'm going to take a slight detour into the notion of a vector space. How many of you have heard of the term vector space? Anybody? Has anyone heard of the term vector space? A few have, right? So there's a conventional notion of a space. The space is a geometric construct with a certain number of dimensions. For example, the 3D space that is, the room that you're currently in, and every object that is in that space lives in. So the room would be a 3D space. This is what you think of a space, as a space. But mathematics also has a concept of a space. A vector space is basically an infinitely large set of vectors which has the following properties. It has one vector in it, which is the zero vector, which has the effect that, which is essentially something that you think of as having no value at all. Now, the set also has included with it an operation, namely an addition, and the set is closed under addition. What I mean by that is that if I take any 2 vectors in the space and I add them up, which is to say I perform the addition operation on those 2 vectors, the result is still going to be within the set. If there's a notion of a multiplication by a scalar. So if I take any 2 vectors x and y, I can multiply each vector by a scalar, and the result is still going to be in the set. And if I perform the operation ax plus by, that is also going to be in the set. So because this addition of any 2 vectors is also going to result in another vector, this has the property that if for every vector x, there's a corresponding vector minus x, such that x plus minus x gives you the 0 vector. Every vector has the additive inverse. Now, these are the basic properties that we look for to decide if something is a vector space. If you add any 2 of them, the result is still in the same space. If you scale anything by a constant, the result is still in the space. And corresponding to every vector is the additive inverse, such that when you sum the 2, the result is a 0 vector, which is also in the space. There are some additional properties like there's a scalar multiplicative identity element, addition is associative, addition is commutative, and so on. These are additional properties, but just considering these should tell you most of the story. And so here's an example of a vector space. 3 component vectors any vector of the form x, y, z, where x, y, and z are real. Now, is the sum of any two such vectors also a vector in the set? What do you think? Tianyan. Is the sum of two vectors of this kind also in the set? Tianyan? Yes or no? Anybody else? Abhishek? If I take in,
Can you hear me?
yes. Yeah. So is the sum also in the set?
Yes, the sum of two vectors is also in the set. Addition should be closed under.
Yes. And the zero vector is part of the set. I can have the 0, 0, 0 vector, right?
Yeah.
And scaling by a constant remains in the set, right? And every vector has an additive inverse. So this is a vector space. Here is another definition of a vector space. Now this, we are always used to thinking of vectors as arrangements of numbers of this kind. Here's something entirely different. So here, maybe I can draw this. I'm thinking of things of this kind where I have my axis, which goes from, say, minus pi to pi. And I'm thinking of things which are drawn between minus pi and pi. So this is a function between minus pi and pi. And the function has the specific property that where is this? That the function has the form a times cos x plus b times sine 2x, where a and b are real. Now, is this a vector space? Can anybody tell me? If I take two such functions and add them up, will the result also have the same form? Yes or no?
If you add them, the result should have the same form.
Is the zero vector part of the set?
Yes.
Because a and b can be zero, right? And does everything have an additive inverse?
Yes, when A and B are just the negatives of what they are.
And so here you have a vector space, except it's not an arrangement of, it's not a collection of numbers, it's a collection of functions. And still it forms a vector space. That makes sense to everybody? Okay, lovely, right? I got at least 3 yeses. So now here we have the definition of a dimension of a space. Every element in the space can be composed as the sum or some linear of some other elements in this space. For any, if I take any x, any vector x in the space, I can always write x as, so as the sum of two other guys, which is fairly easy to show. I can just write as x equals 2x plus minus x. And we know that both 2x and minus x are in the space. So every vector in the space can always be written as the sum of other vectors in the space. This is trivial to prove. But then a vector space has these special subsets such that if I know this subset, every vector in the space can be expressed as a linear combination of the elements of this subset. So for example, I might have x, y, and z over here, and then I can consider any vector in the space, and every vector can be written as some a1x plus b1y plus c1z, or some a2x plus b2y plus c2z. Basically, every vector in the set is a linear combination of these three guys. The smallest such subset, such that every vector in the set can be expressed as a linear combination of the subset. The size of the smallest subset is the dimensionality of the space, and the elements of the subset are called the bases. So in this example, if I assume that I cannot have any subset that has fewer than 3 components, such that every vector can be expressed as a sum, then the dimensionality of this space is 3, and specifically x, y, and z are going to be the bases of this space. So let's consider some examples. Over here, suppose I take the set of all vectors of the kind x, y, z. What is the dimensionality of this space? Anybody? Abdul Hamid, what's the dimensionality of this space?
3.
3. And what are the bases? Can you come up with bases?
The standard basis, namely 0, 0, 1, 0, 1, 0, and 1, 0, 0.
Perfect, right? Easy. Now here's another vector space. This is the set of all vectors that can be written in the form a times 1, 2, 3 plus b times 4, 5, 6. First, is this a vector space? If I take any two elements of this kind and sum them up, will the result still be in the set? What do you think, Vidur?
Yes.
Okay. Does this include the zero vector?
Yes.
And does every vector have its negation? I can just replace a by minus a and b by minus b, correct?
Yeah.
So every vector also has its negation, right? So is this a
Right.
vector space?
Yes.
What is the dimensionality of this space?
2.
Just 2. I just need 1, 2, 3, and 4, 5, 6, and I can construct every vector in the space. So although every vector element of the vector has 3 components, the dimensionality of the space is 2. This is in fact a subspace of S. So you get the idea, right? What a vector space is. So here is an example. Again, this is a poll, but I'll ask you guys to answer. What is the dimensionality of the space? Can you answer in chat? What is the dimensionality of the space? It's 2, right? I just need cos x and sine 3x, and I can construct every vector, every element of the space. And we know that this is a vector space. So you've got the idea immediately. Okay, so much for math. I'm coming back to reality now. So we have the notion of dimension. There are 2 interpretations of dimension. One is the spatial dimension of a vector, which is the number of components in the vector. And an n component vector lives in an n-dimensional space. But there's the embedding dimension of a vector, which is the dimensionality of the subspace of the vector. So here, for example, these guys, they have a spatial dimension of 3, meaning they had 3 components. But the embedding dimension was only 2, which meant that although they had 3 components, all of the vectors lay on a 2-dimensional plane. So is the distinction apparent to you guys? Yes or no? Right. Just type yes into chat. I can follow, right? So, all right. So beautiful. So much for vectors. Let's move on to matrices. First, let me ask somebody here. Isaiah, what do you understand by what a matrix is?
A 2 or more dimensional ordered set of numbers.
A matrix is 2-dimensional. If you go to higher dimensions, it's a tensor, right? A matrix is a rectangular or square arrangement of numbers. So this, for example, A, which is, it's a 2 cross 3 matrix. It's got 2 rows and 3 columns. This is a 3 cross 3 matrix, not 3 cross 2, right? So you get the idea. Now, so that a matrix has dimensions. It's rectangular. So the matrix size is specified by the number of rows and columns. This one here, this looks like a vector, but it's also a matrix. It's got 3 rows and 1 column. This is also a matrix, although it's a vector. It's got 1 row and 3 columns. This is a 2 cross 2 matrix. This is a 2 cross 3 matrix. And this Pac-Man over here is in fact a 321 cross 399 matrix of numbers that's being visualized. So that's a basic definition of a matrix. Let's look at some operations. There's the notion of transposition. When you transpose a matrix, all of its rows become columns and columns become rows. So the transpose of ABC, this column vector, becomes this row vector ABC. The transpose of a row vector becomes a column vector. The transpose of a 2 cross 3 matrix is a 3 cross 2 matrix. And this is a picture of my good friend Chris Wren, who's at Google. And this is what he looks like when he's a regular matrix, but if I transpose him, he ends up looking like the picture to the right. You get the idea, right? So, sure, a matrix is a rectangular arrangement of numbers, right? But what is it? If I just give you a rectangular arrangement of numbers, it doesn't really tell you anything. A matrix only becomes informative through its relationship to vectors. It's a beautiful concept. The information in a matrix is about how it relates to vectors. So, in fact, there are three different views that we can take for a matrix. You can view a matrix as a transform. You can view a matrix as a data container. And you can view a matrix as a compositional building block of vector spaces. So let's look at matrices for transforms. Here's a matrix. You know, this matrix A is a 3x4 matrix. Now, we all know what it means to multiply a matrix by a vector. If I apply this matrix to this column vector B1, B2, B3, B4, this matrix transforms this vector. Specifically, it transforms this vector B1 to B4 in this manner. The result is now a 3-component vector, where the first component is A11 times B1 plus A12 times B2 plus A13 times B3 plus A14 times B4. The second component is the same operation, A21 times B1 plus A22 times B2 plus A23 times B3 plus A24 times B4, and so on. So this is a left multiplication. You multiplied the vector from the left by the matrix, and this transformed this four-component vector into a 3-component vector. So again, the number of components in this vector must match the number of columns, and the number of components in the result is going to be the number of rows in the matrix. So this is typically thought of as converting something in the row space, because the number of elements here is the same as the number of rows. Sorry, in the column space, because the number of elements here is the same as the number of columns, into the row space, because the number of elements in the result is the same as the number of rows. Now, if your matrix is a row vector, then you can transform it by right multiplying it. If your vector is a row vector, you can transform it by right multiplying it by a matrix. And so again, we know this operation, B1, B2, B3, it's a row vector. When it's transformed by this matrix, the result is now going to be a 4-component vector. I'm showing it in transpose because I couldn't fit it on the slide, but the first component is simply going to be B1 times A11 plus B2 times A21 plus B3 times A31, and so on. Now, these two operations, I'm sure all of you are very, very familiar with. I don't need to get into it. But what does it actually do, right? Here's what happened. Let's say you had an original vector and you transformed it with this vector, with this matrix. This vector ended up as a new vector in a different position with a different length, right? So now consider this matrix. Suppose, look at the circle. Suppose you can think of every point on the circle as a vector. If I were to transform all of the vectors on the circle using this transform, this figure is going to change. What will it become? How will the matrix transform the circle? Anybody?
It will be a bigger circle.
Be a bigger circle. Anybody else want to guess? Vishal? What will it become? Vishal, what will it become? I can't hear this. Karan, what will it become? It's going to become an ellipse. Let's take a look, right? This is what it does. Here is your original circle. I've color-coded it to show the individual points on it. Here's your matrix, and the two row vectors of the matrix are also shown as vectors here. This matrix is going to transform every point on the circle to a new point, and the result will be an ellipse. It's a linear transform. It's going to convert circles to ellipses. This makes sense to you guys? Yes or no? You can just type yes, right? Okay. Questions? Any questions? Okay. So now I have two axes over here, right? You can think of the matrix as not just transforming the circle, you can think of this matrix as transforming every point in the space. And this results in a new space, right? If that is the case, I have some coordinate axes over here. I also have coordinate axes x and y over here. How do the axes in this new space relate to anything in the original space? Can anybody tell me? Anybody want to take a guess? What would it be? Anyone? Yanbing? Do you have any guess? I think Yanbing's muted. Somebody else. Cynthia. You want to take a guess?
Would it just like multiply the base of the original by y?
It's actually much simpler than that. You see these two rows over here? These two row vectors? They are shown by the orange line and the blue line. The new x-axis over here is going to be the vector that's orthogonal to this first row vector. The new y-axis over here is going to be the row that's orthogonal to this orange line, the second row vector. That makes sense? So I can just look at these two vectors, and the vectors that are orthogonal to these two guys are now going to be the new axes. It's easy to prove. If I were in the classroom, I could show it. Does that make sense? Yes, no. Can you even get, or are you willing to accept this as religious belief for now? Yes or no? Okay. Aisha says yes. What about the rest of you guys? There's just two of you. What about the rest? Jin Shang, Alfaraj. Would you be happy with this? So here is what happens, right? I can maybe try to do this with a pen by writing it, and I'll show you why it is the case. If I can get my pen. In the new space, the vector, this guy is, say, 1, 0, right? And this is going to be some matrix, which is your transform, times some vector, correct? So what does this mean? The second component is 0, which means this vector is going to be orthogonal to this vector. Is it not? Yes or no? Right. So in other words, the vector that's orthogonal to the second vector is going to be a new x-axis. The vector that's orthogonal to the first vector is going to be a new y-axis. Does that make sense? It's very easy to understand, right? Once you actually see it. And so the same thing applies in 3 dimensions. If I were to transform a 3-dimensional space using a 3x3 matrix, the new x-axis is going to be the vector that's orthogonal to the second and third rows of the matrix. Basically, it's going to be the vector that's normal to the plane, hyperplane that's formed by the second and third rows. The new y-axis is going to be normal to the hyperplane that's formed by the first and third rows. And the new z-axis is going to be normal to the plane that's formed by the first and second rows. Did that make sense? Using the same logic, right? It's simple, right? Once you think about it, it's not very complicated. It's actually fairly simple. Questions? Did that make sense, Ching Shang? I'm just trying to. All right, I'm assuming it did. Okay, so what we just saw, that matrices can be thought of as transforms. They're transforms. But then matrices have a second meaning. Matrices are also data containers. How so? Think of this matrix. This matrix R, I can think of it as a stacking of two rows. So in this case, this matrix is a container containing two row vectors. So also, the same vector can be thought of as a horizontal stacking of the vectors AD, BE, and CF. So this matrix is also a data container containing three column vectors. So matrices can also be data containers. That make sense? Yes
Yep.
or no? Yeah. Question? Okay. So we use that all the time. For example, if I have an audio signal, these are often represented as spectrograms. The x-axis is time, the y-axis is frequency. The brightness at any point represents the energy in that frequency at that time. This collection of numbers is actually a matrix where every column is actually the spectrum of one small segment of the audio signal. So we can represent spectrograms as matrices, but this matrix is actually a data container, where every column represents a spectrum of one segment of the signal. Similarly, images. I can just think of the image itself as a matrix, but then, here, every row over here represents one row of pixels in the image. It's a data container. So if I can have, for example, these three notes. I can represent each of these by a spectrum. So now that each node is a vector, and my data container is going to just have three columns, one representing one for the spectrum of each of these three nodes. And this matrix is a data container for these three nodes. Or I could have a collection of face images. And if I unraveled each of these images into a vector, then this matrix is a data container where the columns represent all of these facial images. So the matrices can be data containers. Questions about this? Matrices as data containers. Any questions? No? Okay. And the final bit is matrices can be compositional building blocks for vector spaces. How is that? Now consider this matrix A. When I multiply this matrix by this vector B1, B2, B3, B4, what is the result? The result, in fact, is B1, the first element, times the first vector in A, plus B2 times the second vector, second column of A, times B3 times the third column of A, plus B4 times the fourth column of A. So multiplying this matrix by this column vector basically mixes the four columns of A to give you a new vector. So by doing this, this matrix contains the vectors such that when you multiply it by vectors, it generates new vectors which are spanned by these four vectors. So the matrix generates the space of vectors that can be formed by mixing its own columns. That make sense?
Yes.
Okay. Please type yes, in the chat box, so I know, right? This is when I'm right multiplying. I could left multiply. So if I take the same matrix and left multiplied it by B1, B2, B3, this is going to be B1 times the first row plus B2 times the second row plus B3 times the third row. It's going to be mixing the row vectors. It generates the space of row vectors that can be formed by mixing its own rows. So how does that, help me? Think of this matrix as this container of these three nodes. If I multiplied it by this vector 1, 2, 1, the result is going to be 1 times the first node plus 2 times the second node plus 3 times the third node, which gives me the mixture of the three nodes. So the matrix enabled me to generate this mixture and every other mixture of these three nodes. So also, right? If I had these two images, this is a telescope, the Arecibo telescope, I think in Puerto Rico, and I had this Pac-Man, I could unravel both into these vectors. So this is a 40,000 cross 2 matrix. And then if I multiply this by any column vector, it's going to mix these two images to give me this third image, which is some kind of a vague combination of the telescope and Pac-Man. So here are the three interpretations of a matrix. It's a transform that modifies vectors and vector spaces. It's a container for data vectors, and it generates vector spaces. Questions? Okay, I assume not. So now we've defined vectors and matrices. Let's look at some operations. First, let's look at the outer product of two vectors. If I have a column vector, I can multiply it from the right by a row vector, and the result is going to be a matrix where the first column of the result is the vector multiplied by the first element of the row vector. The second column is this vector ABC multiplied by the second element. And the third one is ABC multiplied by the third element. Easy enough. So from a signal perspective, what does this mean, right? What kind of an interpretation can this guy have? This is basically modulating this column vector by this row vector. So for example, if I have this node over here, and I want to modulate it across time using a sinusoid, then this node is going to be my column vector. The sinusoid is going to be my row vector. And then when I compute the outer product, that gives me the spectrogram, which is. So the outer product computation is basically the modulating the vector, the column vector by the row vector. And here's a physical interpretation of it. This makes sense? Right. Okay. Now, what happens when I multiply two matrices? We know this very well, right? If I multiply this matrix A by this matrix B, then we know what the result looks like. This corner element is going to be the A11 times B11. You're going to be multiplying all the elements of the first row over here by the corresponding elements of the first column and summing them up, and that's going to give you this corner element. For the second element, you'll be multiplying all the elements of the first row by the elements of the second column, and that gives you the second element, and so on. So the ijth element of the result is the result of multiplying the elements of the ith row of the first matrix by the jth column of the second matrix, element-wise, and summing them up. So everybody's familiar with this equation, right? Yes, no? Okay, this is easy, right? But here's a different way of thinking about it. And so this is really beautiful. Let me do this with a pen. Now look at this matrix, right? This matrix I can think of as having as a data container. So now, or a vector builder, right? So I can think of every column over here as a vector. And so I can call this A1, A2, and so on, right? And so now I get A1, A2, AN. Similarly, I can think of this guy as a collection of row vectors. And so this is B1, B2, Bn. This makes sense? What about the rest of you guys? This makes sense? And now just applying the inner product rule, what will the result be? What is the result going to be? Anybody? So does anybody want to answer what the result is going to be using just the inner product rule that we just saw? Like how? What do you think? What is the
A B.
This is going to be A1, B1,
Yeah.
A2, B2, AN, BN, correct?
Yes.
This makes sense to everybody? Please type yes or no if it did. Yes, okay. So this is so beautiful. Why? Right, or here I'm actually looking at it differently. So I'll skip to this. That's this guy over here, right? So what this means is that this matrix product is going to be the sum of the outer product of the first matrix and the first column of the first matrix and the first row of the first matrix, plus the second column of the first matrix and the second row of the first matrix, and so on. This makes sense? Now, how many of you are familiar with this idea? If you've seen this, if you are familiar with this, okay, do me something. If this is something that you haven't thought about before, let me know. But it's not very commonly understood, right? And the same thing, I can think of the row vectors over here as my vector. I can think of the columns of B as my vector. And then when I think of it this way, here's the result. This is exactly this, right? This is like my, in this case, I'm going to have, this is A1 through AN times B1 through Bn. And so the result is going to be A1, B1, A1, B2, and so on, which is this guy here. So you can think of if I think of the data, think of matrices as data containers, then I can just apply scalar math, and I'm still going to end up with the same matrix multiplication rule. Questions? This makes sense? Both of these? It's beautiful, okay? But then let's look at this one so this one again, right? The product of these two matrices is going to be the sum of the outer products of corresponding columns and rows. So, for example, if I have these three notes, and I want to generate a sound where the first note is modulated like this first sinusoid, the second note is modulated by the second sinusoid, and the third note is modulated by this third sinusoid, I can just create this modulation matrix where the first row is the first guy, the second row is the second guy, the third row is the third guy. And then the product of these two matrices is actually going to be, component-wise, the sum of component-wise multiplications, right? The first column times the first row, which will give me the second column times the second row, which will give me this. The third column times the third row, which will give me this. And so just this little matrix multiplication gives me this composite effect. So did this make sense? Do you how we set this up, right? So simple. The power of thinking about things in terms of matrices and vectors is something else. So here, for example, suppose some of you might have seen these cheesy old black and white movies from the 40s and 50s where they have fade-ins and fade-outs. And so let's say you want to create a little video where you start off with a telescope and the telescope fades out linearly, and you want it to fade into this Pac-Man linearly. Here's what I would do. My first column is going to be the telescope. The second column is going to be my Pac-Man. The first row is going to be the fade out of the telescope. The second row is the fade in of Pac-Man. And so now when I just do an outer product, the matrix multiplication of these two guys, consider the first one. The first column multiplying the first row is going to give you the telescope fading out. It's a matrix. And the video showing the video of the columns of this matrix. Similarly, the second row second column multiplying the second row is going to give you the fade in of Pac-Man. And so these cheesy 1950s fade ins and fade outs are basically just simple matrix multiplications of this kind. Right, questions? Any questions? Okay. And so matrices have, you can perform matrix operations. For matrix summation has this property that you can changing the order of the summation does not change the result. So what is this property called? Anybody remember? What's this property called? If A plus B equals B plus A.
Is that commutativity?
Pardon me?
Commutative?
Commutativity. Right? Exactly. And A times B plus C equals A plus B times C. Right? I mean, A plus B plus C equals A plus B plus C. This is associativity. Matrix operations have this property. Same thing with matrix products, right? The product of A, B, and C doesn't, the result is going to be the same no matter how you group it. It's distributive. A times B plus C is AB plus AC, but it's not commutative for multiplication. AB is not the same as BA. And because A is going to be one rotation and B is going to be a different rotation. And so, rotating a paper left and then rotating it up is not the same as rotating the paper up and then rotating it left. You'll end up with completely different pictures. And then you have the transposition rule. The transpose of A times B is B transpose plus A transpose. So this is something that we're actually going to see quite a bit somewhere during the course. So this one here is worth remembering. Okay. So I have a little poll over here. For the first one, anybody want to tell me which properties are true for matrix multiplication? Does the transposition property hold for matrix multiplication? Yes, no, there's only one answer. What about the rest of you guys? Is it distributive? Is it associative? Is it commutative? No, okay. And what about the second question? A plus bx equals b plus ax. Is this true or false? It's true, right? Easy. Lovely, okay. Here's a magical property of matrices. The set of all matrices of a given size is actually a vector space because it's closed under addition. If I sum two matrices of a given size, the result is a matrix of the same size. If I multiply a matrix by a scalar, every element gets multiplied. It's still a matrix of the same size. The zero matrix exists. Matrices have additive inverses. Associativity and commutativity rules apply for addition, which means that the space of matrices is in fact a vector space. So a matrix, amazingly enough, is also an element of a vector space. It is a vector. So we just gone through various definitions. Just a little bit more. We'll look at various matrix types. The identity matrix, also called the lazy matrix. It's a matrix which does nothing. It's a do-nothing matrix. If you operate on a space using the identity matrix, the result is the same space. The identity matrix has elements 1 along the diagonal and 0 elsewhere. Then you have the diagonal matrix, also called the scaling matrix. So this diagonal matrix is like the identity matrix in that it has 0 elements off diagonal, but the on diagonal elements can be non-zero, and each element scales one axis. So here, for example, this 2, 0 matrix, when it operates on the space, it's going to stretch the space along the x-axis by a factor of 2. and along the y-axis by just a factor of 1. So it's a scaling matrix. If this number is negative, it can also flip it left to right or top to bottom, depending on which dimension has the negative sign. And then now we also have the permutation matrix. The permutation matrix simply rearranges the axes. For example, if I have this permutation, now the permutation matrix has this property. Every row is going to have a bunch of zeros and just one element, which is 1. And if it's a full permutation matrix, then each row is going to have a different entry, which is 1. And this has the property that when it operates on a vector xyz, it just rearranges the components to, for example, this permutation matrix operating on xyz results in yzx, right? It effectively permutes the arrangement of elements in the vector. A rotation matrix. So if I take any vector xy and rotate it by theta, you end up with a new vector x prime, y prime. What is the relationship between x prime, y prime and xy? So if you think about it, it's easy to show, right? Does anybody know how to derive this particular relationship here? Anyone? How would you do this? It's easy enough. So let's say this length is L, then this x prime equals, and let's call this alpha, right? Is going to be L times cos theta plus alpha, which is going to be L times cos theta cos alpha cos theta minus L times sine alpha sine theta. And L cos alpha is just x, L sine alpha is just y. So easy. So this is simple, right? And so the relationship between the coordinates of the rotated vector and the original vector are given by this formula here. This can be expressed as a linear algebraic operation, which says that x prime y prime is going to be some r theta times x, where r is the rotation matrix, which says that the vector is rotated anticlockwise by theta, or alternately the space is rotated clockwise by theta. This makes sense to everybody? Yeah, okay. So more generally, if you take any matrix operation at all, every matrix operation is probably a combination of one of these 3 operations: rotations, permutations, and stretching. You take any matrix at all, and I can always express it as the combination of a rotation matrix, a permutation matrix, which has only elements of 1s and 0s, and a scaling matrix, which has got only diagonal entries. So this is an amazing property, right? If you think about it, any transformation of a space that's linear is going to be a combination of a rotation, scaling, and permutation of axes. So just intuitively, although the proving this is a little less non-trivial than just intuiting it, this must be obvious to everybody. This making sense? Okay. Beautiful, right? Okay. So now let's look at matrix properties. I'm going to stop with matrix properties. I'm going to go and we'll cover the rest of these topics in the next class. Okay. Now consider this cone over here. If I transform the space by some matrix P, that transformation is going to modify this cone. Let's say the process of transformation eliminates one or more dimensions. So for example, it takes this cone and squishes it into this 2-dimensional object. The full dimensional object over here has lost a dimension. So any transformation, any matrix that causes objects to lose one or more dimensions is called a rank deficient matrix. So here's an example of two examples of rank deficient matrices. This matrix to the left, if it operates on this cone, it's the three-dimensional cone, it's going to squash it to this two-dimensional object over here. So this is rank deficient. So also this guy over here, if it operates on this cone, it's going to squash it onto just points on this line. So it has reduced it from 3 dimensions to a one-dimensional object. So this too is rank deficient. And what is the rank of the matrix? What would the rank of the matrix here be? Anybody? In this case, what's the rank of this matrix? 2. The rank of the matrix is going to be the dimensionality of the resulting object when it operates on a full dimensional object. So this is 2. So here, the rank of this matrix is 2. It's started on a 3-dimensional object and reduced it to a 2D object in 3D space. So this matrix has rank 2. This matrix converted this object into a one-dimensional object. So this matrix has rank 1. And now, this makes sense? This makes sense, guys? Yeah, okay. So now here, we were speaking of square matrices. What about non-square matrices? So here, for example, if I've got 3-dimensional data, I've got to say this sphere, which I'm representing as this 3-dimensional matrix, because every point on the sphere would be an entry here. This sphere can be if it say it's transformed by this 2x3 matrix, the result is going to be in how many dimensions if the sphere is transformed by this 2x3 matrix? What's the resulting dimension? Anybody? What is the result going to be? If I transform the sphere by this matrix here, what will it be? Come on, guys. This is easy. What's the dimension? It's going to be 2, right? I'm multiplying every 3-component vector from this point by this 2x3 matrix. So the result is going to be a 2-component vector. The sphere is going to become a two-dimensional object. It's going to get squashed. The entire 3-dimensional space is going to end up as a 2D space. And in that 2D space, that sphere is going to get squashed into an ellipse. That makes sense? Right. Now let's go the other way. Suppose I start with this 2-dimensional space. I can multiply this 2-dimensional space and every element on it by a 3x2 matrix, correct? If I multiply this guy and transform this guy by a 3x2 matrix, how many components will the resultant vectors have? Anybody? If I multiply this, how many components will it have? If I multiply, come on, guys, it's going to, if I multiply a 2-component vector, say AB, by this one, x1, x2, x3, y1, y2, y3, the result is going to be 3 components, is it not? What about the rest of you? Aisha says yes. What about the rest of you guys? What do you think? Right? So you've gone back into 3-dimensional space, but have you really? Will this squashed ellipse become a sphere again? Yes or no? No. What will it be? It's going to be a disk, an elliptical disk in the 2-dimensional elliptical disk in the 3D space. This makes sense? So there's another way of thinking about rank. We can think about it in terms of bases. I'll stop right here because we're quite out of time. But then for the first question, given a circle in R3, there will always exist a matrix M such that the image of the circle under the transformation will be a sphere. Is this true or false? False. A square matrix with n rows and n columns will always have rank n. True or false? Also false, right? Is I can take a square. We saw examples of a square matrix which squashed a cube into a line. Actually, do you guys have a couple of minutes? There's a final interesting topic. I'll just assume the answer is yes. Okay, Ken, I'm going to pick one of you. Right. Let's say Yanbing. What do you understand by the determinant of a matrix? What do you understand by the determinant of a matrix? Is Yanbing here? No. So I don't think Yanbing can hear me. Somebody else. So let me ask again, Abhishek. What do you understand by the determinant of a matrix? Abhishek? Somebody else want to answer?
One of my understandings is that if the determinant of a matrix is 0, it also means that it can't be full rank.
Yes, but geometrically, what does it mean?
The volume of kind of like a shape that the matrix forms.
So, okay, so typically when you think of a determinant, here's how it's defined in your school and college, right? You can compose, if it's a 2x2 matrix, you can compose a parallelogram of its vectors, and the determinant is the area of this parallelogram. If it's a 3x3 matrix, is this parallelepiped, and if the determinant is this volume. But does that give you any idea of what it physically does to the space? In terms of the space, what does the determinant mean? Anybody?
How much it's scaled or like shrinked.
Exactly, right? If I take a object, say a unit sphere, and I transform it by the matrix, this object is going to change and is going to have a new volume. The ratio of these two volumes is the determinant of the matrix. That make sense? Right. So what about the rest of you? That makes sense. So here it is, right? The determinant of a matrix is simply the magnitude of the determinant of the matrix tells you how much the volume of any object in the original space is scaled by. And so if the determinant is 0, it means the object is going to lose one or more dimensions. Matrix determinants are only defined for square matrices because they characterize volumes in linearly transformed spaces. Rank deficient matrices have determinant 0 because they compress full volumed n-dimensional objects to 0 volume objects. And conversely, all matrices of determinant 0 are rank deficient because they compress full volumed objects into 0 volume objects. And from this, you can intuit the properties that in terms of determinants, although matrix multiplication is not associative, is not commutative, in terms of determinants it is, and it's also associative. So the determinant of A times B times C is the determinant of A times the determinant of B times the determinant of C, because if you're scaling it by some A, then you're scaling it by B, then you're scaling it by C, it doesn't matter. You're scaling it by A and B and C. And it's commutative. If you're taking a unit volume object, first scaling it by a factor A and then scaling it by a factor B, then it's the same as first scaling it by the factor B and then scaling it by the factor A. The shape of the object may be different in the two cases, but the volume is going to be the same in both cases. And of course, this doesn't hold, right? Does this make sense? The determinant of the sum doesn't, it's not the sum of the determinants. Okay. All right, guys. So I'll stop right here. Thank you for your patience and thanks for coming in for the class at this time. I'll stop the recording. How do I stop the recording? I'm going to try to stop the recording. Is there a way to stop the recording? Stop sharing. I don't seem to be recording. All right.
Here's a
Yeah, here's the thing, right? Stop.